In this video, I will demonstrate how to create a COMSOL Multiphysics model with a geometry from SolidEdge synchronized through LiveLink for SolidEdge. I will model the resistive heating of a bus bar made out of copper. The bus bar conducts electrical current from bolt A to bolts B and C, and it's cooled by natural convection in the surrounding air. In the model, I will study how the temperature increase depends on the size of the design by applying a geometric parameter sweep over the width and length dimensions. To conduct current in an energy-efficient manner, I want to keep the temperature increase of the device to be less than 30 degrees above ambient. While setting up this simulation, I will go through the following steps: finding the dimensional parameters in the SolidEdge design, initializing the simulation in the model wizard, synchronizing the geometry and parameters, defining the materials and the physics, configuring the solver, and evaluating the results. While modeling with LiveLink for SolidEdge, both COMSOL Multiphysics and SolidEdge are running on the computer to allow for the geometry synchronization between the programs. The assembly, which I've already opened in SolidEdge, consists of the bus bar and the connecting bolts. In SolidEdge, I will find the variables to control the length and width of the model from COMSOL. Right-click the bus bar part in the SolidEdge Pathfinder and select Edit. On the Tools tab, click the Variables button to get to the variable table for the bus bar part. The variables V631 and width control the length and width dimensions respectively. Remember these variables for later because they will need to be entered manually into COMSOL. Now I can close the variable table dialog box and return to the assembly by clicking the Close and Return button. Now I can switch to COMSOL and start setting up the analysis in the model wizard. 3D is selected by default, and we'll choose Joule heating for the physics. Select a stationary analysis and click Finish. In the Model Builder, I start in the Geometry section. For this model, add LiveLink for SolidEdge to synchronize the geometry. Click Synchronize, and the geometry appears. To be able to control the dimensions of the geometry, I enter the variables for the length and width in the CAD name column of the Parameters section. Make sure to specify which part the parameters came from by adding .busbar.par to the name. Without this extension, COMSOL won't be able to find the parameters in SolidEdge. In corresponding rows of the COMSOL name column, I enter the names of the global parameters in my model that are to be linked to the SolidEdge variables. As the COMSOL parameters are not yet created, I will do so by right-clicking Global Definitions and adding parameters. Type in the very same parameter names you have entered in the settings of the LiveLink node. To check that the synchronization works, I'm entering larger values than the current dimensions for the length and the width. Now, to trigger a regeneration of the geometry in SolidEdge, I build the LiveLink node. The regenerated geometry is transferred back to COMSOL. This new bus bar becomes a lot larger. Click the Zoom Extents button to fit it inside the graphics area. To set up the physics analysis, I need some additional parameters, which I import to the Parameters node. Use the Load from File button below the table to do this. Two parameters are added to the table. One is the heat transfer coefficient for the convective cooling boundary condition, and the other is the voltage applied to the bus bar. I can now move on to choose the materials for the bus bar and bolts. Right-click the Materials node and open the Material Browser. For this model, I will add titanium for the bolts and copper for the bus bar. Now set up the boundary conditions. First, I find the convective cooling boundary condition. I apply it to all the outer boundaries except the 3 connecting surfaces of the bolts, which I am excluding from the selection. Before moving on to the next step, I also need to enter in the heat transfer coefficient, the parameter HTC. Next, I select the ground surfaces for the current conduction problem, the faces of the two lower bolts. The last boundary condition to set up is the electric potential, which is applied to the upper bolt. I type in the parameter name for the applied voltage, V tot. Now I will add a domain probe, which can be found under the Definitions node. I'm adding a domain probe to monitor the average temperature increase in the device. I will change the expression to give the increase from ambient 20 degrees Celsius. A default normal size mesh will automatically be generated, so I'm skipping the mesh section and moving on to configure the parametric sweep, which I add to the study node. The parametric sweep can sweep over any parameters defined in the parameters node under global definitions. To specify the parameters for this sweep, I click the Add button below the table. This adds the first parameter to the table, the length. Use the Range button to define the range. I'll start at 60 with a step size of 20 and stop at 100. Add the second parameter to the sweep, which is the width of the bus bar, and define a range from 40 to 80 with a step size of 20. One more setting is left before solving, as I want the sweep to include all combinations of the specified parameter values. To compute the sweep, right-click the study node and select Compute. During the sweep, COMSOL solves the model for each parameter combination and updates the results table with the evaluated temperature increase. I can follow this process in a plot. For each new parameter combination, the values are synchronized with SolidEdge, where the geometry is rebuilt and synchronized to COMSOL. Back in COMSOL, the sweep is almost done, and I can see how the temperature increase lowers for the larger dimensions of the bus bar. To get a better view of which combinations of parameters keep the temperature increase in the desired range, I create a surface plot of the table. With the length and width parameters on the two axes, I can see which combination of values gives a temperature increase below 30 degrees. To get an even clearer view, I can limit the data range to 30 degrees. This shows the plot only where the temperature increase is below 30 degrees. For more information, visit our website.